In this video, I want to take a look at examples of subspaces. Now, it turns out every vector space has two subspaces at least, right? And the first one here is what we call the zero subspace. So any vector space V, let W be the set which contains just the zero vector. Now, it has only one thing in it, but it by itself is a vector space. And it is a subspace because by checking, take any two things in there. Well, there's only one thing in there. There's the zero vector, there's the zero vector, and there's the zero vector. Those are the only two things you could add together, and they add up to be the zero vector, which is in W. So yes, axiom 1 is true. And then you could say take any scalar multiple of the zero vector, and that will be the zero vector. So it's closed under scalar multiplication. And that is a subspace of any vector space. Right? Whatever vector space you're in, the set that contains just the zero vector in that space is a subspace. Now, the other subspace is kind of a funny one because it's just the whole space. Right? If I let W be the whole space V, well, then certainly it's closed under scalar multiplication and it's closed under vector addition. So that would make it a subspace. Anyway, here's some other ones. In Rn, let V be any non-zero vector. And then I look at the subspace of all the things that look like KV, where K is a real number. In R2 or R3, or Rn, that looks, the vector V looks like a vector. And then when I multiply it by any scalar, that is, if this is at the origin, then the scalar multiplication just generates a line. That is, and it generates a line through the origin. So actually, it turns out in any Rn, the set of all lines through the origin, any line through the origin is a subspace. Right? Just one line through the origin is a subspace. Likewise, if I had two vectors in Rn, and I take all the linear combinations of them, that is k1v1 plus k2v2, where k1 and k2 are real numbers, then, well, for instance, if k1 and k2 are 1, then you'd look at, this vector here, but any combination, it turns out you're generating a plane that goes through the origin. And I know it goes through the origin because I could take k1 and k2 both equal to 0, in which case this would give you 0 plus 0, which would be the zero vector. So this would be planes through the origin. Lines through the origin are subspaces, planes through the origin of subspaces. The textbook that we have just does this in R2 and R3, but it's true in Rn as well. Now, it turns out that in R2, the subspaces, there's only 3 different types. There's the zero subspace. Of course, every vector space has the zero subspace. Then there's lines through the origin. Any line through the origin is a subspace by itself. And then, of course, there's all of R2. So there's the zero, there's lines through the origin, and there's the whole space. In R3, you've got more things. You've got the zero, you've got lines, any lines through the origin, and you've got planes through the origin are also subspaces, and then you've got the whole of R3. So there's 4 types of subspaces in R3. When you move up to R4, you've got lines, planes, and whatever 3-dimensional things are called. Hyperplanes, spaces. Anyway, those are the only things. Now, let me ask a question here. Is R2 a subspace of R3? Now, we are so used to calling R3 by the variables, the coordinate system x, y, and z, where we call R2 just x and y. And we think of this xy plane as the plane that's down here. So it is very tempting to say that, yeah, R2 is a subspace of R3, but it's not. Because if you take an element of R2, it looks like an x comma y, right? It's a vector, x comma y. In order to be a subspace of R3, the things in it have to be things in R3, but they're not, because this has only got 2 elements in it, and everything in R3 has 3 elements in it. So stuff down here in the xy plane actually has coordinates x, y, 0. It's not stuff in R2. It's stuff in R3 that just happen to have all their z coordinates equal to 0. So is R2 a subspace of R3? No, it's not, because the stuff in R2 is not in R3. Now, granted, it has subspaces that look just like it, but they're different. They're different because they've got this last coordinate. Here's an example. In R1, so just all the numbers, is the set of even numbers a subspace? Well, certainly if you take 2 even numbers, right? So if you take 8 plus 12, they add up to an even number. So axiom 1 is true. That is, it is closed under vector addition. And if you take 2 evens, you get an even. However, if you look at axiom 6, scalar multiplication, it's not the case, because if you take the number, R1, the vectors are all numbers. So if I take the number 8 and I do scalar multiplication with the, let's say, the scalar 1/8, I get 1. But 1 is not an even number. So scalar multiplication is not closed. In fact, you get even worse by just, multiply by the square root of 3 or something like that. You don't even get an integer, right? So although it is closed under addition, it is not closed under scalar multiplication, and this is not a subspace. Now, when I look at vector spaces, the vector space of, let's say, n by n matrices, so square matrices, square n by n matrices, there are several subspaces of note. In particular, diagonal matrices. If you add 2 diagonal matrices, you're going to get another diagonal matrix. If you multiply a diagonal matrix by a scalar, it's still diagonal, right? So those satisfy axioms 1 and 6, and diagonal matrices are a subspace of the space of n by n matrices. Likewise, upper triangular matrix. If you add 2 upper triangulars, you get an upper triangular. If you multiply upper triangular by constant, it'll be still upper triangular. Likewise, lower triangle. And symmetric, right? Symmetric matrices, if you add 2 symmetric matrices, you get a symmetric matrix. If you multiply by a constant, then it's still symmetric. So each one of these is a subspace of n by n matrices. I want to point out that invertible matrices are not a subspace. Because, for instance, let's just do 2 by 2s, right? I know that 1, 0, 0, 1 is an invertible matrix. It's the identity matrix. It's its own inverse. Also, I know that the vector minus 1, 0, 0, minus 1 is invertible. But if I add them together, I get the 0 matrix. Well, maybe I could have just started with this for my argument. But the 0 matrix is not invertible. Now, that's going to be a problem because I have to have the 0 matrix. But so anyway, this kind of shows a couple different things. One is the addition is not closed, and it doesn't even contain the 0 matrix in this thing. So the set of invertible matrices is not a subspace of the set of n by n matrices. Okay. And lastly, I just want to take a look at sort of a telescoping sequence of subspaces. Take for your big space here the space of all functions. And I'm thinking of these as functions that are defined on, let's say, the whole real line. Okay. Now, as a subset of those, there's the set of continuous functions. Now, certainly not all functions are continuous because you got your step function and you got your tangent or things like that have vertical asymptotes and stuff. But some functions are continuous. And it turns out that if you add 2 continuous functions, the result is a continuous function. And if you multiply a continuous function by a constant, you get a continuous function. And so this is a subspace of the space of all functions. Now, C1 is the functions that have a continuous first derivative. So in order to even have a derivative, you've got to be continuous to start with. So C1 is a subset of C. And to have a continuous derivative, I know that if I add two functions with derivatives, that the derivative of the sum is the sum of the derivatives, and so I get another thing with a derivative in it, that the sum has a derivative. And likewise, if you multiply a function times a constant, then the derivative is the constant times the derivative of the function, and so that would exist as well. C2 is the set of functions that have a continuous second derivative. So you can take the first derivative, you can take the second derivative. In order to have a second derivative, you should have had the first derivative to begin with. So this is a subset of C1. And then you can go all the way down to, functions that have infinitely many continuous derivatives. So each one of these is a subspace of the previous one, coming down to C infinity here that have everything. So all the derivatives. So like sine and cosine would fit in here. Sine x, cosine x, not tangent. Tangent doesn't even fit into there, but e to the x fits in there. And in fact, all the polynomials. Right? In particular, if you pick a particular n, say 7, these might be polynomials of degree 7 or less. They are a subspace of C infinity, which is a subspace of all the way down the line here. Okay? So there's this whole nest of functions that, spaces of functions that are subspaces of other stuff. Okay? So there's a bunch of examples of subspaces for you.